Welcome to today's lecture. We're going to be talking, I'm Dr. Ray. We're going to be talking about 3D printing. First of all, we're going to talk about what is it, and after that, what can you do with it. Got a very short video of CAD, the way CAD should be, with Elon Musk. And then after that, we're going to talk about the additive and subtractive processes. What are they and what are the differences? And then, of course, after that, we're going to talk about the 3D print methods. Three of the most common 3D print methods. There are, as the technology gets more advanced, there are more and more different ways to print 3D. Now, so it's really hard. When I first began preparing for this lecture, I realized, the information, it gets outdated so quickly. And we'll talk a little bit more about that as we move on through the lecture. Okay, well, what is it? The best way for me to explain what it is to show you. And I've got a clip that's put out by GE. But before we watch that video, let's talk a little bit about the vocabulary that we will see in that video. And also we will be using throughout this lecture. Additive manufacturing, that's another word for 3D printing. And that is basically, instead of taking the material away from a, say, block or circle, instead of removing, kind of like if you think of a sculpture or statue, you start with a big block and you take it away until you get what you want. Additive, that's subtractive. We'll talk about that later. Additive manufacturing is different. You just build what you want layer by layer until the object is complete. And of course, each layer is a teeny tiny, slightly different shape. Okay. We'll talk about the word, we'll use the word process. Some of these words I'm sure you know, but just to be sure. We're talking about the process. When we use the word process, we just mean to do something step by step. It's more than just, how to say, turn on the light is not a process for getting ready. Let's say, okay, turn on the light is not a process. But if I'm getting ready for bed, now we got a process. I have to, I have to brush my teeth, prepare my clothes for tomorrow, and turn off the light. Okay. Just turn on the light, turn off the light is not a process. But if it's part of something bigger, it's a process. And in this case, another way to say step by step. Physical object, just something you can touch. Most of the design we do as engineers in our computer, that's not physical. We might be building physical objects, but we really can't touch what's inside the computer screen. Anything outside the computer screen is a physical object. Okay, there's my cell phone. It's a physical and it's an object. Most of the time we just say object. Physical object, something I can touch. Digital design, let me say that again. Digital design or CAD, computer aided design. We'll talk more about that later. This you cannot touch. Okay, we might be making physical objects, but it's in the computer. We're going to hear the word slice and layer a lot, and they're really not different. You can see this bread. The bread has been sliced. That's a verb. The bread has been sliced. The bread is in slices. Now that's a noun. We have 1, 2, I don't know how many we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 slices. That one is one slice. One slice, 10 slices. You're going to hear the word manufacturing. To make something by machine or at a factory. That's a kind of a simple definition that will work for us. Layer, okay, layer is just like slices, but usually when we say layer, we, not necessarily, but in our case, it's going to be talking about it this way. And it's also more, usually, you know, we're talking about thinner than, just very thin. Okay, well, there it is right there, sorry. Thin slices stacked on each other. Metal powder, that's metal. Rather than melting metal and trying to reshape it, we have ground. Ground is a process to make something, you know, you just keep crushing something till you make it smaller, ground, into a powder. Now a powder, you go and it will fly away. That's a powder. Melt, we'll use the word melt. In our case, we're talking about melting metal until it becomes a liquid. But for this example, we're just going to use a ice. Melt means to go from a solid, ice, to a liquid, in this case, water. We'll be using the word laser a lot. And laser, I don't know, trying to explain laser, just look at the picture. We've got a light laser. It's not exactly a burning laser. And here we've got an example of a laser burning wood. I don't know if that's just a Photoshop or if that's real, but it doesn't matter. You get the idea. With lasers, we can melt things. And that's the important part. And we're going to be talking about, you're going to also hear the word durable. But now you will hear that just in this video. But anyway, you're an engineer and everything you make should be durable. That means long lasting. Long lasting, not easy to break. It is durable. If you're an engineer or technician of any sort and you don't build things or make things that are durable, even software, it has to be durable. If you don't make things that are durable, then you shouldn't be in this business. You're going to hear the word precise. Now, also put the word precision in here because you will hear it used in both ways. Precise is exact. It's be precise. It's an adjective. Precision is a noun, and you will hear it used in both ways. And it's pronounced differently. Precise, precision. Precise, precision. And it just means more exact or very detailed. Okay, precision. Every small part has to be perfect. You're going to hear the word complex geometries. Complex geometries. Now, geometry means shape, and we've got a shape over here. That is a simple shape. Over here, we've got the same. That's a cube. It has a cubic shape. It's a cube and it has a cubic shape. This is a cube, but it's a complex cube. It's really probably hard to see on this video, but it's really made up of interlocking pieces, almost like some sort of welded chain links all put together. And that makes it complex. Okay. The word revolutionizing, which means well, the best thing for me to do is just tell you completely new, or something that will change the world. Okay, we had the industrial revolution, we've had the computer revolution, we've had the information revolution, and now we're in the field of printing anyway. We're in the field of manufacturing. We're having a new revolution on how to do things. Okay, so let's get on with what I promised you. What is 3D printing?
What is additive manufacturing? Additive manufacturing, also known as 3D printing, is a process that creates a physical object from a digital design. An engineer designs the object using computer-aided design, or CAD software. The 3D design file is then sliced into thin layers and uploaded to an additive manufacturing machine. The manufacturing process begins once an extremely thin layer of metal powder is spread across the platform. A heat source, such as laser or electron beam, then melts the first layer of the 3D design. The platform is lowered, and another layer of metal powder is spread across the platform. The layering and melting process is then repeated until the part is complete. The metallic powder is removed, and a physical object is revealed. Additive manufacturing allows you to produce parts that are lighter, stronger, and more durable than traditionally made parts. Build times are faster. Engineers can add precise features and complex geometries without increasing cost. In fact, additive manufacturing is revolutionizing the way we work.
Okay, and we certainly want to thank GE for that video. Let me make sure my player has stopped. Okay, sorry. It's supposed to stop on the last frame, but it did not. So there's an idea of what 3D printing is. Moving on, what can you do with it? Okay, let's see what we can do with it. I'm going to show you video. It's just easier for me to show you videos than if I use my we're gonna see, wow, what are we gonna see? Prosthetics of when somebody loses an arm, they need a new arm or leg in the field of medicine. We'll see construction and a few other things, but it's so much easier for you to see than to for me to try to explain. Here we go, part 2. I hope it works. All right, in this video, this is the field of medicine, or the medical field. Even though they're not making medicine, we call the field of medicine or medical. And here you see they're using SLA, I believe this is. And there we have our bone that we can use to help people with broken bones. I'm not sure if that's a model or we've actually really found a way to implant bones I'm not sure. But anyway, there we made a bone. And that should be just about the end of that section. And here we are seeing part of a wall. In this case, we're making a staircase, steps. And that is concrete, cement. Sometimes we say concrete, sometimes we say cement. And here we're looking at prosthetic arms. I forgot to turn off the subtitles, but that's okay. A little look at using 3D printers to make prosthetic devices, which certainly really helps people's lives, like this young lady here. And the next one is pharmaceutical, or this is also medicine or the medical. But actually, when we're talking about medicine, we actually say pharmaceutical. And the precision of 3D printing can help with medicine's subscriptions. They have to be, they can get it a much more precise prescription, which can be customized, we'll talk about that, and individualized for each person, but also not just as more accurate. To make a pill with 3D printing is more accurate than the traditional method, but it can be customized or custom made. And of course, if we have little children, they just might like to have a smiley face or a heart. So there we are using 3D printing in the field of pharmacy or pharmaceutical. And these guys are gonna build a rocket. They're gonna actually build the entire rocket by printing. Awesome. And here we have just traditional manufacturing, where we need some, I can't remember if these are automotive parts or airline parts. But they're parts necessary for a complicated machine, and they have to be very precise. They are usable parts, not in this case. They're made from metal. They're not prototypes. They're not examples or samples. They are useful, practical, functional. And as you can see, there it is. And then a look at some of the other kinds of parts: automotive, titanium in the aerospace, that means planes, aluminum, titanium, medical, there's a medical device, a sensor, and dentistry. I know that went by kind of fast, but the fillers in your teeth, sometimes you need the whole top of a tooth, and that's an example of useful, not just prototyping. Now, in the beginning, when 3D printing first came about, it was new and very expensive. And it was a way of prototyping. And I hope I have the word prototype in my lecture, in my PDF. But that just means before I really manufacture a lot of something, I want to test it. Before I can test it, I need to make a real example. And that real, for example, think about the arms that we saw. I need to make an example to see if it works before I start making 500 or 600. That's not a good example because those arms are custom made or customized. But anyway, I think you have the idea. If I'm going to make an airplane part, before I make 100 or 500 or 1,000, I want to test it. That's called prototyping. Okay? And that's what 3D was first used for. But now it has become very practical. We can not only use plastic. Most prototypes were made from plastic, a plastic resin that can get hardened. But nowadays we can fuse metal together, which is an amazing process also. And we'll see some of that. And so here we go on to the next. Get my screen back up there. CAD. Now before we do anything, we have to design it in CAD. Okay. That is computer aided design, as you can see. Its purpose is to build models. Now when I say models, I don't mean physical. There's that word again. I don't mean a physical object. Excuse me, I need to have a drink. I don't mean physical object. I mean visual. Visual means to see, a visual object. So first we have to design it visually, and we can run computer models. I mean, we can take a part for an aerospace engine, and we can put that part in the engine, and we can run a simulation. Remember we talked about simulations in the first lecture that I gave. But that's all visual, and it's in the computer. But we got to start somewhere, and that's where we're going to start. And it's got to be exact, because this model, this is going to be a finished product, and the information that the 3D printer needs will come from our CAD design. It's going to read our CAD design. It's going to make a product. So that CAD design has to be good. It has to be perfect, of course. It has to be perfect, as you know. Now, this is the traditional CAD design that most of us are used to. We make three-dimensional objects, but it's definitely, for us, it's, two-dimensional. We use a mouse, and we click on buttons, and we add shapes, and we rotate things. But I'm going to show you a video clip next, which is, I think, pretty cool. It's Elon Musk showing how they use CAD in the space industry. I guess we'd call that, aerospace. Anyway, the space industry. So let's take a look at that video. Right, let me make sure that's where I am first. Yeah, after CAD, as I said before, after CAD, we need to make a prototype. There we go. We did make a prototype. Okay, so in the process, first we make a prototype, then we make the real thing. Okay, so a prototype is a model for testing new ideas before production, before we actually make them. And here's that video from Elon Musk. And let's take a look, hopefully.
Right now we interact with computers in a very unnatural sort of 2D way. And we're trying to create these 3D objects using a variety of 2D tools. And it doesn't feel natural, it doesn't feel normal the way you should do things. So we started playing around with the idea and using a few of the things that are available out there, such as the Leap Motion and Siemens NX, which is what we used to design the rocket. And we wrote some code to kind of integrate the two. And we started off with what you see here, which is a wireframe of the Merlin rocket engine. And what I can do is I can go and grab it, and I can rotate it in multiple dimensions. And then what I can do is I can put another hand in there, and I can zoom, or I can zoom in and out on the wireframe. And then I can also translate it. So I can move it around the screen, and then zoom and translate. And this is what we started off with a few months ago. And then you can also spin it, and then catch it. So this is kind of a fun way to interface with what is really a very complex model. Now we'll go from this to what we're able to advance to a few weeks after the wireframe, which is to actually use a full 3D CAD model of the engine. So here what you're seeing is the actual interaction with the CAD software manipulating the real 3D model of the Merlin engine just using hand gestures. If you can just go in there and do what you need to do, just understanding the fundamentals of how the thing should work, as opposed to figure out how to make the computer make it work, then you can achieve a lot more in a lot shorter period of time. So then we went to a 3D projection. We started off with the kind of 3D projection that you're familiar with in the movies, where you use 3D glasses. We also did a freestanding glass projection, which is what the sort of technology that was used in the Iron Man movies. And then finally we used the Oculus Rift, which is immersive virtual reality that actually tracks your head position, and you really are moving around the object. It feels like it's right there in front of you. Now let's use this for an actual component on the rocket, which is a cryogenic valve housing. You can really apply your intuition and take something from your mind to a physical object with far greater ease than we currently do. Now that we've gotten the object out of our head and into the computer, how do we get it out of the computer and into reality? So we're actually going to print this with a 3D laser metal printer. So the way that the 3D printer works is it lays down fine particles of either titanium or Inconel, and then it goes over it with a laser and melts those tiny particles onto the prior layer. So it builds it up like just layer by layer. So I believe we're on the verge of a major breakthrough in design and manufacturing, in being able to take the concept of something from your mind, translate that into a 3D object really intuitively on the computer, and then take that virtual 3D object and be able to make it real just by printing it. So it's going to revolutionize design and manufacturing in the 21st century.
So there was that word revolutionize again. It's going to revolutionize the industry. So that's CAD, the Elon Musk way, or I should say the SpaceX way. That's the company. And I just thought about, wow, what kind of toys Elon Musk must have. If you don't know Elon Musk, he's the founder of Tesla cars, Tesla Automotive, and SpaceX. I imagine he's got so many electronic toys and stuff we all wish we had. Okay, that's the future of 3D though. if they're doing it at SpaceX now, or this was even quite a few years ago when that video was made, but there'll be someday we'll all be operating like that. Technology is great, isn't it? All right, let's move on. So now that we've talked about 3D printing, oh, and you saw Elon Musk, I'm sorry, that the video was to show you how they use CAD, C-A-D, but also they did a 3D print right at the end. So we're going to continue with 3D printing, and another word for 3D printing is additive or additive manufacturing, additive processes. So we've got the additive and subtractive processes, and we're going to compare them. Now, I had thought about adding a third component to my lecture also, which is molding or casting. And this is when you start with a mold or a cast, and you fill it with very, very hot metal, or you can fill it with hot plastic, whatever. And then afterwards you've finished, you have a new shape, and you throw away the mold. The problem with that process is you've got to make the mold first. And then you've got to make the mold where you can use it. You want to use it more than once, hopefully. But some molds you can only use one time. Some molds you can use again and again, but eventually they will start to wear and you will have to make a new mold or cast. Okay. And then here's just a picture and I didn't make it big enough. That is a box, a metal box. The liquid is going into the box, which is like something like this, and making its own shape. Now, subtractive is when we start with a block and we slowly take away the block until we get the shape that we want. Additive, on the other hand, is we start at the bottom. As far as I know, every additive process or 3D printing process starts at the bottom and builds up. At any rate, it starts at the bottom and it makes, heard the word layers, even layer by layer. And it adds those layers, and each layer, as you can see, is a different shape until we get the final shape that we want, or the final shape that we desire. So the next thing I'm going to do is show you again. It's much easier for you to see than for me to try to explain. We're not going to talk about anymore about the casting, formative or casting processes. We're not going to talk about that anymore. We're going to talk only about additive and subtractive processes compared. So let's move to the video, next video, so you can see the subtractive process. We start with a block and simply shape that block, taking away, it's subtracting, take away or subtract what you don't want until you get the object that you want. Okay, and then the next one is now that was a subtractive process. Now we're going to go to the additive process. And you can see we start from the bottom and we add layers until we get what we want. And that is I can't remember, that is that's the FDM process there, I believe. Talk more about that later. And here is the I believe this is I'm not sure which process this is. We better watch. The CAD, we're starting with CAD. We're designing what we want in CAD, and the CAD will break the SLT form. This is an SLT file. It will break that CAD into, as you can see, into levels so that we can send that information to the machine. Here's an example of the filaments being heated, and there we go. So this is the additive process. You can see instead of starting with a block and then ending up, you start with something and you end up with the shape that you desire. But in this case, we start with nothing. We actually start with nothing. I mean, we have the materials, but the materials in the actual frame, the materials are outside the frame of operation. Okay, in the subtractive, we start with a block. It's in the frame of operation, in the frame of process. But these are outside the frame of process, or the platform, for lack of a better word. So you start with nothing and you build one layer at a time. Now we're going to next compare, I believe is where we are. Let me see. We're going to compare them. In additive manufacturing, just so you know, it's layer by layer. And to make a solid 3D product, we've already talked about that. There's that word layer. Layer by layer. Okay. What we're making is a solid, physical 3D product. Subtractive manufacturing is layer by layer. Material is removed, subtracted, not added. But it's not a true layer by layer process, because you can come at it from many different angles. Think of it more like a layer as the earth has layers. But you might go, when you're subtracting, you might go through several layers at a time and then move over to several layers at a time. So it's not a true layer by layer process like when we truly print only one layer at a time. In additive manufacturing, we have to have materials that have a low melting point. They've got to get hot enough. They've got to be able to melt. And in this case, such as plastic. In the subtractive manufacturing, we can use any kind of material that we want. It doesn't have to have a low melting point. If something has a too high melting point, it's hard to control. So we need a lower melting point usually. Subtractive, we start with any kind of material. It doesn't matter what the melting point is. We're going to keep it as a solid. We're going to move in the additive process. We're going to, in one process, there's another one. We use powder and we fuse powder together. But in the original design, you needed something either already melted or you're going to melt it when you use it. The density can change during the printing process. The density can change. Okay. In subtractive manufacturing, you start with a piece of material and that density is the same all the way through. Okay. Now, if you want to know what density is, I've got it's taking the same amount of cubic space and having different amounts of molecules or materials. So this is, the more I can squeeze into that space, the higher the density. This is compared to these two, that would be a medium density. And of course, the last one here is a low density. The molecules or materials, depends on what size object you're looking, cube that you're looking at. So there we go, from high density to low density. And again, that word is density. Get back to the point though, the additive process. Because it's being made layer by layer, we can just do all kinds of complex designs, and we can use more or less of the material in any one place. Additive manufacturing uses less waste, makes less waste, produces less waste. Any unused materials can be recycled back into the process. Now, I don't mean you're going to put it in the recycle garbage for the recycle people to come and take away. I mean the actual process. Once you finish that process, you take the material, you put it right back in to be used again. It's different. The materials in subtractive processing produce a lot of waste, and the materials cannot be recycled. What we mean is they cannot be immediately recycled. It doesn't mean they can't be recycled in some other way, but usually they're not going to be recycled back into that same quality. It can, but not usually. Additive manufacturing can design very complex shapes. We talked about that before. We've already talked about the complicated or the complex cube and the simple cube. But when we make complex shapes, not only do we mean things that might link or shapes that are not straight, but we also more particularly mean hollow channels or hollow inside, like little tubes or canals or pipes. When they come out, they're already made. If you're going to try to do that in subtractive processing, then you're going to need extra processes to make something like that. Now, it can make some complex, as you can see, surface shaping. That's definitely a complex shape, but it's a surface, not a very complicated design all the way through. Okay. Additive manufacturing is applicable to a narrow range of materials. Fewer materials can be used in the additive manufacturing or the 3D printing. Remember, every time I say additive, I'm talking about 3D printing. However, now these are different kinds of metal powders and ceramics and glass and what else? Other kind of plastics, of course. Now, the process of subtractive manufacturing can we can use a lot more different kinds of materials. Because as long as you can find it, as long as you can, it can be punched, drilled, or cut. I should have said punched, cut, or drilled, but that's okay. As long as it can be punched, drilled, or cut, then we can work with it. And all we have to do is have the hardest tools for that material, harder tools than the material. So, but I do want to say, however, that narrow range of materials for additive manufacturing, that is changing very, very fast. I mean, not many years ago, we could not do metal in the 3D printing. I want to say additive, the additive or 3D printing process. But now we can use metal as well as plastic. Additive manufacturing is best suited for custom designs, and that's what I was talking about earlier. Special circumstances, special situations. Aerospace industry, jets and airlines need very particular parts for their machines, very unique, not the same, different. Anytime you have to make something that's different from everything else, then you need custom designs. And in this case, with the custom designs for prosthetic limbs, that is good in that we can design it to fit that one individual more precisely. Okay? And of course, subtractive manufacturing is more suited for mass production. And that means we're going to make a lot. Okay, we want to make a lot. And today, before the end of the day, our factory is going to make 500 pieces of something. Interchangeable parts, I didn't put that up there, but I should have. For example, common parts. These are what we call interchangeable parts. They would be common across many industries, and we want to make a lot of them. Now let's talk about 3D printing and the types of 3D printing. Now the technology is moving fast. There are not only these three, but there's more. But even these three, the way each of these threes are being done, as a simple, well, I don't want to say that the machinery and the competition of companies trying to make new ways to 3D print keeps the technology moving forward. So these are three good examples of 3D printing. The first one is fused deposition modeling. Okay. Basically, it melts plastic or anything that's meltable. I don't think we've done metal yet, but we melt plastic, and it is a lower price if you're just getting into the 3D printing business, but it has the lowest resolution and accuracy. Now let me be clear, it doesn't mean it doesn't have good resolution, and it doesn't mean it's not accurate, but of the other processes, it has the lowest resolution and accuracy. The other is SLA, stereolithography. And stereolithography was actually the original. If it's the original, I'm not really sure why I put it second, but it's the original form of 3D printing. It uses lasers to cure Photopolymer resin. Okay, what is photopolymer resin? It is melted plastic. It is plastic that is in a state of liquidity. It is in a liquid state. There's like we see water, you have water and you want to turn it to ice. Well, in this case we have wet plastic, so to speak, liquid plastic, just sitting there, all liquidy. We're going to use a special process to make it hard. We'll talk about more about what that means later. And FDM, you can think of it like a glue gun. I mean, when we use glue guns, if you're crafting something, you take a little glue and it's a hot gun. You push the plastic through, you force the plastic out, and you glue things together. Now that's a little oversimplistic, I know, but at least that can get your mind there. SLS, selective laser sintering. That's where we start with the powder. Things come in powder. We can join that powder in many ways. We can add it with a resin. We can mix it with a resin that will harden, or we can compress it. We can put a little on the shape and compress it till it, at the molecular level, it will bond and join together. Or we can use what's probably the best way, I think, is fusing with lasers or heat, in which you put one layer down and then another layer of powder will fuse with the bottom layer by heat or lasers. This is for industrial grade use. If you're in this industry, you've got to learn the word industrial grade. That means serious business. It's not a hobby. I'm not going to be making toys. I'm going to be making things that need to work. They need to withstand pressure. I'm going to do heavy work, hard work, industrial grade use. And these parts could be as strong as those made in injected molding, which we talked about molding before. Now, FDM uses a thermoplastic filament which is heated to melting point. We talked about that before. And then extruded, which means pushed out, layer by layer, to create a three-dimensional object. I like to say it in simple English. It pushes melted plastic through a nozzle and makes a shape from the bottom up. Okay? Nozzle. Here's your nozzle. Here is your filament. Filament is just another word for thread, string. Okay? And that's a spool. It's a spool that's actually on rollers, but it is a spool of plastic string or threads. Let's take a look at FDM in use. Alive. It will be much better for you to understand. I forget what this guy is doing. He's making chess piece, I believe. That, I believe, is the wrong video. This is FDL. I think we've seen this already. I think I jumped ahead by accident. So since we've already seen this, well, let's take a look. Okay, again, that's the CAD. and the SLT file. And now we're going to feed that into the machine, and now the machine is going to print. There's your nozzle, there's your heating element, and we're going to print layer by layer. And you can see how complex this is. You can see the hollow parts and the columns, the dots and triangles and circles. Very, very complex from the inside out. Complex from the inside out. Okay, now we're going to move to the SLA. And now it won't let me go to the next one, so I'm going to try that. Like I said, this was the first 3D printing process. That was the original 3D printing process. He's going to make a simple chess piece. You can see the light there, the actual laser, I mean, hardening. It's making the plastic hard. We call that resin. We don't call it plastic, we call it resin. And this is a good example. It's computer simulated, but it'll give us an idea of what's going on. It makes one layer hard. Once it gets hard, it's got to work all the way to the middle. Then it's going to move down. You can barely see that it moved down. It's going to push another layer of resin over the top. And it's going to keep doing that. And the platform is going to move down until we get a finished piece. Okay. Of course, each time it has to push the resin that we weren't able to see. And here it is coming out of the resin once it's finished. And then there's, now that's the, it's still made from the bottom up, but the platform is being lowered into the resin. We're going to look at another SLA where they work upside down, and they instead of push they pull the model from the resin. Okay. They turn the bottom upside down. There's the lasers. You can see the laser flashing and making the resin hard as they pull it out. But it's still made from the bottom. It's still made from the bottom. Okay? Still bottom to top. Okay? Every process that I'm aware of makes the design from the bottom up. Okay, and that is an example of SLA. I got ahead of myself there. I'm so excited. Let me see. Getting back, we were talking about FDM with the hot plastic and the nozzle, and FDL. And just to show you that was the FDL. I don't know, I could forward, but I don't really know how. Don't worry about that. And then this is the SLA, and we're going to talk about that right now. SLA 3D printing process, that's the one I said that's original. We've seen it, we just watched it. It was the liquid plastic that we use the laser to harden, to make it hard. in the shape that we need, layer by layer. We have liquid resin. We have to have a container or some kind of a tank or box to hold the liquid. This one is the traditional method. This one is bottom up. The bottom is up and it's pulled. Okay. This one is lowered. This one here, as it goes down, every layer is built, it goes down into the resin until the resin's completely covered, and then it comes out. This layer here, it starts at the bottom still because it's upside down, but it pulls the object out of the resin. Okay, and I've already shown you that video. And the final process, which I think is probably the most exciting and the future of the industry, is SLS. And it uses a laser to melt powdered material. Powdered material. Again, powder is when you take something and you grind it into like salt. It's smaller. I know everybody knows salt and sugar, right? It's finer, smaller than salt and sugar. That's powder. If you actually really had powder in your hand and if you sneezed, haichu, that powder would come back in your face. Salt and sugar, maybe a little bit, but it's not going to come flying back up. So that's powder. Powder. And we're going to take different materials, different kinds of powder, ceramic, plastic, and metal, which is really exciting. I think if my research is correct, titanium, which is supposed to be one of the hardest substances known to man, and of course aluminum. And they'll fuse together into, fusing, that's the English, fusing them together. Now this technology is actually part of what we call laser power bed fusion. That's because there's more than one. SLS is just one of the ways. Because we talked about compressing. You can actually compress or use resin to glue. A special kind of resin to glue, but the laser powered and the compression are probably the strongest ones. I really should research that. So, but SLS is one part, and we've got a video for that. And let's see if I can bring that up. I forgot to show you the SL bottom up. Did I? Or did I? No, I showed you this one. Okay. So we're moving on to SLS. We've went from CAD and we put it in the machine, and now that's metal powder. And that light is sort of melting or fusing that metal together. It's very precise. Here we're doing one level at a time. The levels are probably thinner than that. This is just a computer simulation, sorry. Now this is the real thing. That metal is very fine layer. And there's our finished product. Okay, so a little bit about 3D printing, and I believe that is the end of my lecture. Let me make sure I don't have another page, and I don't. I hope you learned something, but mostly, you learn a little bit of English. You don't worry about learning everything at one time. You just see things in the beginning. Eventually, you will see it again and again until it becomes a part of your vocabulary. And that is the end of this lecture. Thank you for watching.